Now start speaking about the Tafel line. So basically, what are the Tafel lines? Tafel lines are basically a different way in which we can design the function, the Butler-Volmer function, in a more smart way that can even extremely interesting in order to allow us to evaluate the exchange current. In which way? So in which way the Tafel lines are an approximation of the Butler-Volmer that allow us to obtain the exchange current? Well, let's remind, for instance, what is a classic Butler-Volmer plot. So looking at the relationship existing between the current density and the overpotential, maybe something like this. If now we want to design this not in a plot that is the overtension versus the current, but maybe overtension versus the module of the current density, or even just current, what is happening is that in this case, since we are basically rotating these types of part in the positive section, since this is a module, we can appreciate a result that is something like this. So we have our potential, we have our current, or yes, something like this. So the module of the current and here the potential, and we can appreciate something like this. This is nothing different with respect to the plot we have previously seen, but we are considering in this case not anymore the current, but the modules of the current. Now the Tafel lines basically are an approximation. Imagine that, even if it's true that when we are at very low overpotential, we cannot, or in general when we are at low current, so when we are moving away from the equilibrium in a small way, we are not able to eliminate the contribute of the other reaction. What does it mean? If we are promoting the oxidation, maybe due to a positive polarization, or it could be a reduction due to a negative polarization, we are promoting one semi-reaction in our dynamic equilibrium. But we know that when we are moving away from the equilibrium, basically the systems, even if we are only able to appreciate or the cathodic current or the anodics, it feels about even the not expressed but theoretically present reaction that is not proceeding. So if we are inducing an oxidation, the system feels about a possible to not expressed reduction, the opposite reaction. And this is the reason for which we have this profile. And we are here at very low current. These types of contribute is not negligible. So if we are promoting, for instance, in this case, an oxidation, we have a contribute of a non-occurring reduction, or that actually is occurring in a small way, but is not visible since we are inducing an oxidation that is still present. So if we want to clarify this concept from a graphical point of view, we know that, for instance, if this is the dynamic equilibrium, we positively polarize the electrode in order to promote the generations of this species, but even if we are only able to appreciate the current associated with this reaction, and anodic current, because it's the major contribute, it's also true that we have even a small contribute of the opposite reaction. We are not able to appreciate it, but it's present. And since it's present when we are at a very low current and at very low overpotential, we have this particular trend that is typical of the presence of this contribute. But when we are moving away in a more far way from the equilibrium condition, so when we are exploiting quite high current, well, in this condition we can make the not expressing reaction negligible. So when we are moving in an important way far away from the equilibrium conditions, we can say that this is completely negligible. What does it mean? That we can eliminate, for instance, if we want to promote an oxidation, we can eliminate the term due to the cathodic current, and we are taking in consider only the anodic. Does it mean that from a practical point of view, if we have now for high current only these types of equation, we can say that this is equal to this. Basically, I'm rewriting the Butler-Volmer equation taking consider of the assumption done. So basically we are making negligible the contribute due to the opposite reaction that we are not promoting, since we are promoting a lot to the oxidation. Why? Because we are now working at high current. And when we are working at high current, the contribute of the not expressing reaction that we are not promoting, the opposite one, is so small that this can be negligible. Only when we are close to the equilibrium condition is not negligible, but this should be taken consider, and the Butler-Volmer equation taking consider very well this contribute. In Tafel line we are eliminating this contribute, so we are only considering maybe the anodic current. And so now we can solve it, we can eliminate this, so we can proceed with the logarithm. So I'm starting at the very beginning with conversions in natural logarithm and then in logarithm base 10, and this is. So now we can say that the overpotential is equal to RT. Maybe if you assume that n is equal to 1 for simplicity, this. And so we can say now that this is equal to RT with minus signs logarithm of this one in the properties of logarithmic, and plus and now what we can say is that if we want to treat this as a function, we can say that this is fx equal to q plus m for x. Why? Because we can pass from the previously seen Butler-Volmer plot of the module of the current now in the module of what? Of the logarithm of the current. And so now this plot, it became as composed of line in this way. It's clear that we are eliminating this part that it was previously present in the Butler-Volmer. Why? Because the Tafel line, it makes sense only when we are at a very high current. This Tafel line is basically one line eliminating this contribute, and the other one is basically the resolutions of the other line eliminating this contribute. Basically this is a function, so this is the point in which we are basically colliding. We have the potential, and this is the slope basically. So what is actually we are doing is taking the Butler-Volmer and decomposing the Butler-Volmer, solving as a straight line first this and later this. So we are imagining that the anodic current does not feel about any types of cathodic current, and later that a cathodic current does not feel about any types of anodic current. And so what we can appreciate is something like this, so a trace straight line with respect to the well-known Butler-Volmer trend. And this makes sense, because Butler-Volmer taking consider about the fact that these anodic currents feels about the cathodic currents when we are at very low current, and so we are close to the equilibrium condition, whereas in Tafel line this does not make sense, because we are exploiting situation having high current. But why water warmers are so interesting, Tafel lines are so interesting? Because due to the junction of this line with this line, this point, if plotted here, allow us to obtain the value of the current that is the exchange current. Obviously this is the logarithmic of the exchange current, but from this we are able to obtain the exchange current. So the Tafel line is an extremely important approximation that allowed us to obtain huge interesting parameter as the exchange current.